Okay. Still 1 minute.
Are you all set, Davide?
Mm-hmm.
Maybe we'll wait just 1 more minute before we start. That's okay. All right, so maybe we can fire up now. So our second speaker of the day, we're very happy to have Davide Gaiotto, and he'll tell us about Feynman diagrams in 4D holomorphic quantum field theory. Take it away.
Okay, first of all, I want to thank the organizers for letting me give an online, for letting me participate online to the conference. I'm terribly sorry I couldn't make it in person. Still trying to figure out my COVID travel format. And I also want to thank Sasha for the many things I've been learning from him over the last 15 years at least, from him or from his papers. I've encountered Sasha's work many times and in surprisingly different circumstances in the study of gauge theories, supersymmetric quantum field theories. The first encounter was in studying with Andy and Greg four-dimensional and equal true gauge theories, as the Wall-Crossing properties seem to be encoded in the cluster structure of character varieties and of other Coulomb branches, and many aspects of the coordinate systems introduced by Sasha's work turn out to be to have very concrete physical meaning, as sort of we could build home physical structures just by sort of following the suggestions to the map. And these sort of ideas were very helpful in also studying things like three-dimensional equal true gauge theories, and are still sort of an important thread in the work we are doing on the subjects still now. I also had a lot of fun learning how to think about transcendental functions and about structures which at first look at me completely alien, like symbols, coproducts, and turned out to be extremely helpful in making sense of things like Feynman diagrams in four-dimensional gauge theories. I myself am not an expert in that subject, but I had some fun forays in the study of correlation functions and no polygonal Wilson lines in four-dimensional integral four gauge theories. And where both at strong coupling and Edward coupling would find pieces of Sasha's work floating around, and often apparently disconnected mathematically. If you find again cluster structures, strong coupling, and coproducts of and polylogarithms and transcendental functions at weak coupling. And so inspired by this, I would like to sort of cut down the number of supersymmetries even further and discuss a project in four-dimensional equal one gauge theory, where I would really love to have further insights from Sasha, because I get the impression from the sort of ingredients I see floating around that there might be some things that he might find interesting here. So this is a situation where we have less supersymmetry than before. So these are only four supercharges in 4 dimensions. And that makes the theories physically more interesting, but more challenging to study, because there is less symmetry, naively at least. these are theories that can show phenomena such as confinement or chiral symmetry breaking. And this is the context where beautiful ideas such as cyber duality were developed. And supersymmetry definitely plays an important role in a lot of these developments. There are quantities such as the chiral ring or the superconformal index, which are protected by supersymmetry and allow some calculations, allow some derivations, and have been studied very carefully by the physics community and have informed our understanding of these theories. But something remarkable to me has happened that recently mathematicians have started studying these sort of theories from in perturbation theory from a mathematical perspective, starting with the work of Costello and then several others. And in doing so, they kind of realized that I think we had missed some stuff, meaning there are mathematical structures, interesting mathematical structures, rich algebraic mathematical structures, which are present in four-dimensional equal one gauge theories, and I've simply not seen studied in physics papers. And it's hard to imagine this will have no consequence at all. So I've devoted the last several months of my time and my students' times in trying to figure out what's going on with this topic. And it's fun, and there is both a lot of interest in math, and I think the possibility of some interest in physics to be derived. So the basic idea is to study quantities which are sort of protected by one single supercharge. And the way to do it is to take your quantum field theory and twist it, essentially by passing to the cohomology of an important supercharge. Doing so, you sort of focus on quantities which are protected by supersymmetry, in the sense that are symmetric under the action of this supercharge. And a striking fact is that after you do so, the theory simplifies and becomes holomorphic, meaning that the local operators depend holomorphically on the position in space-time, at least in a cohomological sense, meaning that if you want, the anti-holomorphic derivatives of local operators are BRST exact. So the mathematical progress is that precise theorems that tell you that quantities in these holomorphic theories can be computed with a simplified Lagrangian. And so from a very practical point of view, calculations are much simpler than we might have thought they would be. Furthermore, these theories come equipped with an algebraic structure called an holomorphic factorization algebra, which is a four-dimensional analog of something that should be rather familiar to a lot of physicists and probably mathematicians in the audience, which is the mathematical structures which occur in two-dimensional chiral holomorphic theories, which are vertex operator algebras. So to say this again, in two-dimensional holomorphic theories, which are defined on, say, Riemann surfaces, you get these beautiful mathematical structures, which are vertex operator algebras, chiral algebras. And they have been an enormous subject of study over the last many years. And the striking fact is that four-dimensional holomorphic theories also have similar structures, and that within every four-dimensional equal one gauge theory, there is hidden an holomorphic theory. And so there is a piece of the four-dimensional equal one quantum field theories which have similar features as these two-dimensional holomorphic theories. In particular, they have infinite symmetries, infinite algebras of symmetries. So in two dimensions, you might be familiar with the notion of Virasoro algebra, which is the algebra of holomorphic vector fields, which act by local diffeomorphisms on these holomorphic theories. And perhaps Kac-Moody algebras, which arise from essentially holomorphic currents in two-dimensional quantum field theories. So what's happening in two dimensions is basically that every holomorphic local operator is automatically a conserved current and remains a conserved current when you multiply it by an holomorphic function of space-time. And so every operator in the two-dimensional theory gives you big family of symmetries. And this happens in 4 dimensions too. And so out of the stress tensor, out of flavor currents or other local operators of these holomorphically twisted theories, you get infinite algebras of symmetries. Things like Hamiltonian holomorphic vector fields of C2, or holomorphic, holomorphic position-dependent flavor rotations. And the story is way more derived than what we are familiar with in 2 dimensions. There are generators of cos number 0 and cos number 1. But still, it's a lot of symmetry, and we would like to understand what consequences does it have. And the general strategy we're trying to follow is so an important point is that these holomorphic theories receive both perturbative and non-perturbative corrections. And so what we're trying to do at the moment is to understand the perturbative corrections as a first step. So we're trying to compute pretty much in perturbation theory this factorization algebra structure, in the hope that then we can sort of guess or figure out the non-perturbative corrections to that. It's a bit of a sort of spectral sequence intuition, where you first do the things that are not too small, and then you do things that are smaller. And at the perturbative level, you are pretty much computing Feynman diagrams. Perhaps somewhat unusual or unfamiliar Feynman diagrams, but Feynman diagrams nevertheless. And so a big chunk of this project has been to figure out which Feynman diagrams we need to use and compute them. And then given these Feynman diagrams, you can use them to add the coefficients of these algebraic structures, the differential and the factorization algebra structure, on the space of local operators. So what sort of Feynman diagrams are we looking at? Forgive my poor drawing abilities. I'm just trying to put on the same slide all the ingredients which are needed for the calculation of one of these diagrams. So these are integrals. So what happens is that the same diagram can be used in many different places. It can appear both in the definition of the differential or the vertex algebra structure or whatnot. There are just a collection of sort of master integrals which can be then used in a variety of situations. And what I'm trying to describe is sort of these master integrals. And you have some graph with some combinatorial restrictions I will describe momentarily. And you can think about this graph as sort of living inside a C2. So we're going to integrate over the position of all the vertices except for one in C2 with some holomorphic measure, which is pretty much an exponential with some holomorphic momentum, and the holomorphic top form in C2, and which vertex we keep fixed at the origin doesn't really matter at the end, as long as you keep the holomorphic momentum up to 0. And then we wedge these holomorphic measures with the propagators, which are 0-1 forms, and they're just they are the Green's function from the del bar operator. And the only subtlety is that we sort of introduce an extra shift in the holomorphic coordinates. You can think about this sort of a generating function for an infinite class of diagrams that you get by expanding in power series of these auxiliary shifts that I denote with Z. There is one for each edge. So this is what we're computing. And there is a sum over a choice of all possible ways of marking one of the edges. And then marked edge, you put del bar on the propagator instead of the propagator. So this is sort of the basic ingredients of the calculation. You sum over these diagrams over all possible ways of picking an edge. You take the wedge product of these one form propagators, you wedge it with these holomorphic top forms, and you integrate.
Davide, could I make sure I understand your notation? So the X's and the Z's are all vectors in C2?
Yes, that's right. That's right.
And also, what is the rule when you put the bar and when you don't?
So in one of the edges you put the bar, you're going to sum over which edge you put the bar in.
Mm-hmm.
Essentially, you're taking del bar of the whole thing. I mean, you can take the product of the propagators and then take the del bar of the whole thing. And this is integrated with some UV cutoff and with some IR cutoff. The cutoffs drop out at the end of the calculation, leaving something finite. It's not completely obvious, but and a lot of the analysis. I don't know if you've seen the formality paper by Konsiewicz. A lot of the analysis resembles the analysis in that paper, although everything is holomorphic instead of topological. I will comment more on that. So this is what we are trying to compute. These integrals for using a specific propagator, which is an SU2 invariant, rotational invariant Green's function for the del bar operator. Although if you were to use a different propagator, you would just get a different gauge for the same structure. So you would get an homotopy equivalent factorization algebra, presumably. Now, the combinatorial subtlety I was discussing at the beginning is just that you want to integrate the top form. So that means that the number of edges plus 3 should be equal to the number of vertices on the whole graph, just because this way for example, here you want to have a 0,6 form wedged with this 6,0 form. I mean, you want to have a 6 the X bar, and you have 1, 2, 3, 4, 5 propagators plus a del bar, so that works. And in general, you have the number of edges plus 3 equal to number of vertices. And there is also local constraints that the number of edges plus 3 should be smaller or equal. So it is also supposed to be smaller than equal or equal for every subgraph. And this kind of graphs have a name. They're called Laman graphs. They were studied initially by researchers which are looking for minimally rigid graphs on the plane. Somehow the counting of degrees of freedom works in a similar way. And they are the same graphs which appear in the formality theorem. They are the same graphs that appear in the Webb's paper by Greg and Greg Willett and myself. So there is a formal resemblance between four-dimensional holomorphic theories and two-dimensional topological field theories, which are what occur in this formality theorem and in this Webb algebra paper, except that here we have interesting holomorphic functions integrated over some configuration spaces, while in these topological field theory papers, you found things like just the number of such graphs with some decorations or the volume of some configuration space. Now, an important step of our analysis is the realization that, so you can do this diagram, this study some diagrams in a standard way, meaning you can write down the propagators in a Zwinger parameterization as an integral of the heat kernel from 0 to infinity. You can just do all the forms combinatorics and get some integrand, and it looks horrid at first sight. You can do one loop. 2 loops already looks horrifying. But something rather amazing is that there is a coordinate system which makes a coordinate transformation, which mixes space-time and Zwinger parameters, which makes the integrand completely trivial, but makes the integration region interesting. So we found that we can manipulate these integrals until they become essentially the Fourier transform of a region in the space of loop momenta. So you can take an element in situ for every edge, require that they add up to the momenta at each vertex, so they're essentially the momentum flowing through the edges. And then you can impose this constraint that there are some positive real numbers for each edges, such that if you add up this coefficient times the momentum along each loop, you get 0. This is a bizarre constraint. I could show you the detailed steps on how to get there, but I don't think they will terribly instructive. But it has a flavor that is vaguely related to the amplituhedron. You have this sort of inequalities, sort of strange map between, something which is pretty much the positive part of the projective plane. I don't understand the geometry fully, but the answer, I understand the fact that the answer is the Fourier transform of some kind of curvilinear polyhedral region in C2 to the number of edges. And this curvilinear region has close relationships to some configuration spaces which occur in the formality theorem. And it starts looking much more geometric already. And then the second realization is that these curvilinear regions have all sorts of interesting recursion relations. So you can write down a quadratic relation, which is sort of satisfied geometrically and then satisfied by the Fourier transform. This quadratic relation is kind of funny. You take a graph, which is sort of has one edge more than the ones we are studying, pretty much. And then you look at all possible subgraphs of this graph, which satisfy this Laman condition, and such that when you contract them to a point, what's left also satisfies the Laman condition. So here again, there is a this sort of idea of taking a Feynman diagram and contracting a subgraph has to do with the Hopf algebra of Feynman diagrams. Here, we're looking at some specific terms which have this Laman condition. But anyway, so there is a quadratic relation where you sum over all possible subgraphs of a graph, and you take the amplitude for the subgraph, and you have it act in a certain way, or the amplitude for the graph that is left after contraction.
What is the Laman condition? What is you said yes,
there is this Laman condition, which is pretty much the condition for so suppose you take a web we're studying in our paper, you take away the external edges, what's left is Laman graph. It's a minimally rigid graph on the plane.
Oh, I see. Okay, cool.
And it is sort of such that all the form degrees work out when you do the calculation. And so the way there is an interesting way for this Feynman diagram to act on another Feynman diagram. Essentially, you take the momenta, you shift them by derivatives of the z's for the other diagram, and so you transform one of these functions into a differential operator or a difference operator acting on the other. But it's a relation. And it's experimentally seems to be sufficient to determine the functional dependence of these Feynman diagrams. So we only have studied the problem perturbatively in these shift parameters and only the first few orders in perturbation theory. So I should not make a universal statement at this point, but it looks plausible that one can compute these Feynman diagrams and thus derive the factorization algebra structure for the quantum field theory without ever doing an integral, as long as one can solve these quadratic relations. And I would love to have any insights on the transcendentality of the answer. So any sort of tools that will allow us to process these quadratic relations better. At the very the striking fact is that once you have these diagrams, you get the factorization algebra for every gauge theory. So these are sort of universal coefficients, and then you combine them with the details of your fields and interactions to give a final answer.
I have a question.
Yes.
Are your quadratic relations a repackaging of something like the L infinity relations for these algebras?
So I'm not sure if repackaging is the correct term, but essentially they guarantee the factorization algebra structure. In a sense, they make sure, they ensure that the factorization algebra structure holds Feynman diagram by Feynman diagram. So pretty much as you say, take the differential and you look at differential squared acting on an operator, the differential will have some Feynman diagrams. The differential square will have Feynman diagrams inserted inside other Feynman diagrams. And this relation is telling you that all the terms in Q squared, which have the same topology when you do this insertion, cancel separately.
Yes.
Which is pretty much the only way this could work for arbitrary theories. And it's the same thing that was happening in the Webb paper with Craig and Edward, where again, in that case, you were looking at graphs with specific slopes of the edges. But there would be the same idea that the L infinity or infinity relations would hold Feynman diagram by Feynman diagram because the quadratic relation satisfied by the webs.
Right, the T star T equals it. Yeah. So so you're saying these this kind of allows you to prove the quadratic relations on the algebras.
Yes, that's right. So once these relations hold, you have a holomorphic factorization algebra in situ for every gauge theory.
Okay, thanks.
And right, so and the analogy with the webs or with the factorization, with the formality paper by Kontsevich, as I'm saying, is much more than an analogy. So essentially, in those papers, there are things like the moduli space of ways to put such a graph on the plane, and the coordinate system is the slopes of the edges. And you are integrating some forms on the moduli space of such embeddings. Here, instead of just the slopes, you have slopes and lengths of edges, pretty much. And you're doing a Fourier transform instead of an area. But the graph combinatorics are the same that would guarantee the L infinity, are literally the same that would guarantee the L infinity structure in 2 dimensions. Yes, I mean, in the formality paper, these Feynman diagrams were defined, and then they would turn out to evaluate to 0 in the bulk in the specific gauge that was used there. But it's easy to study a slightly different gauge where the operations would not be 0, and then this sort of identity to guarantee that you have an infinity. Okay, right, and I would love to have analytic answers for these generating functions of Feynman diagrams so that you can just give the factorization algebra structure. At the moment, we just compute them recursively, and then we plug them into Mathematica to compute some differentials and brackets and whatnot. So we can start doing some low-level calculations about this, low-loop calculations about these factorization algebras. Okay. So what do I mean with this factorization algebra structure? So let me be a little bit more specific. So there is a space of local operators, which pretty much it starts its life as polynomials in the fields and the holomorphic derivatives. A good mathematical way to think about it is that you're sort of doing an homotopy transfer or a spectral sequence where you study the free theory first, you pass to the cohomology in the free theory, and then you try to add the interactions in. And when you add in the interactions, the Feynman diagrams are automatically produced as sort of the homotopy transfer. So you have these local operators, you have holomorphic derivatives of the fields, and so you have a lot of possible local operators you can write down because you can write polynomials of the derivatives. And a good way to keep track of them is to use generating functions. So if I look at something that form, A of Z, B of W, and I expand it at Z, I'm essentially looking at things that form A local operators are a good way to keep track of all the derivatives. And then when you compute correlation functions with multi-local operators, that's when you get these sort of funny shifts in the propagators. Because say here I was placing the operator at x2, but actually some of the fields were shifted by some formal parameter so that I can treat simultaneously all the derivatives of the fields. And as I said, you get a four-dimensional analog of a vertex algebra structure. Remember, in vertex algebras, you have the elements of your vacuum module. And for each of these elements, you can get an infinite collection of operators acting on the vacuum module. Simply by taking Fourier modes of the operator. So you take your operator, you integrate around other operators after multiplying it by something like z to the n del z, dz del z. Okay. In 4D, you do something similar. You take an operator A, you do a descent to get the one form, you wedge it with some other form on space-time, and you integrate it on an S3 surrounding another operator. And so this gives you a collection, an infinite collection of symmetries of the theory for every operator. If you do the stress tensor, you get an action of, as I was saying, Hamiltonian symplectomorphisms of C2. Or if you have a conformal field theory, just all holomorphic symplectomorphisms of C2. If you have a current for some type of symmetry, you get a Kac-Moody algebras of some sort. The only subtleties is that in 2D, you have positive and negative modes of your currents. In 4D, the negative modes have Gauss number 0 and the positive modes have Gauss number 1. So it's a bit of an unusual structure. It's more derived and we are comfortable with, perhaps, but it's there. And is worth studying. As I anticipated in answering some questions, right? These Feynman diagrams give you the differential, they give you diagonal operations, and the quadratic relation guarantees associativity, diagram by diagram. Okay. So we've been a bit faster than I thought. We started studying some examples. So we have looked at four-dimensional pure gauge theories, which have sort of only the gauge fields and no matter. And we've looked at QCD, supersymmetric QCD. We have some gauge fields and you have some matter, like you have SUN gauge fields, and you have some matter in the fundamental and at fundamental representation. These are sort of the most familiar four-dimensional equal one theories. So it's reasonable to start looking at those. But perhaps before I start looking at examples, it's worth to stop for a moment and see if there are other questions about the previous slides.
Davide, some parts of this remind me a little bit about higher dimensional BC systems.
Oh, totally. So
are you aware of that? Yeah, you know that work that I did with Nikita and Andrei Losev, or maybe you mean something else by higher dimensional BC systems, but there are higher dimensional, you can define them on Kähler manifolds. And there's a lot
So
there's a holomorphic current algebra associated with them.
So I think there is definitely some close relationships, although I would definitely call the pure gauge theory, for example, a BC system in 4 dimensions. In a BV formalism, so the fields of the theory are sort of forms, and the various 4 components are all interesting.
That's okay.
So that in this BC system in 4 dimensions, like the C field has both the Gauss, those numbers as a 0 forms, and the gauge fields as 1 forms. So I don't think Nikita's theories had gauge fields too, but I might be incorrect. I should look at those papers again. So it's definitely true that holomorphic theories were studied before. I've not seen these Feynman diagrams computed.
Oh, that looks totally new to me. But some other aspects, some other things that you said resonated with that.
Yes, so I think I would like to understand better the relation between those holomorphic theories and the ones that have been studied by Kevin and others. So set up properly, there are definitely very strong analogies between the 2D and the 4D theories.
But you're saying that one can interpret pure, standard, good old n=1 super Yang-Mills theory with no crazy modifications. And in that theory, there's a subsector that looks like this.
Yes, so the holomorphic twist of pure n=1 gauge theories is literally a BC system in 4 dimensions. So it has an action line of B del bar C plus BCC. Plus something that contains the theta angle. And you can do Feynman diagrams in this 4-dimensional BC system, and you will get the factorization algebra structure of the pure gauge theory. And it's a totally remarkable simplification. So intuitively, you can pick every field of your simplified theories and say, oh, this must come from that field of the physical theory, although the correspondence is often not so precise. It's really it's a theorem that there is an homotopy transfer theorem that the full 4-dimensional gauge theory can be simplified to this BC system. And these holomorphic theories, for example, only had the anti-holomorphic part of the connection. They only have.
I'm a little confused when you say it's a BC. I thought it's like a holomorphic BF theory,
which is also a 4-dimensional BC system.
I see.
So,
but I mean, they're bosonic fields, right? But I guess okay, you're just considering.
Yeah, that's right. In this 4-dimensional BC system, B is a boson and C is a fermion. And if you expand out in components the action, you get a BF term.
Mm-hmm.
And sorry. Right. So, for example, when I talk about holomorphic derivatives, so the fields, they're just literally derivatives instead of covariant derivatives because there is no holomorphic part of the connection. But if you go and look at it, what are the BRST transformations of these holomorphic derivatives? They match what would be the supersymmetric transformations of the original physical fields. Another thing that I didn't say, and I should have probably said, is that because most of the audience, I think, is mathematicians, so I didn't want to put too many physics terms. This is a talk about a physicist trying to understand what mathematicians are doing, really, not the other way around. But still, the closest physical analog to these sort of calculations is to think about the semi-chiral ring or the 4-dimensional n=1 theories. Now, I've heard the term semi-chiral ring, but I cannot even figure out which papers I've heard it in. So you can study operators which are cubed by a supercharge in the physical theory, modulo things that are in the image of the supercharge. I can call it semi-chiral ring because physicists are used to study the chiral ring, where you look at things cubed by 2 supercharges, modulo things in the image of 2 supercharges. The chiral ring is not a cohomology, and it's a bit strange mathematically, but it's very powerful. The semi-chiral ring is just much bigger. It has derivatives of operators and so on. But the perturbative corrections to the differential and to the factorization algebra structure are just broad generalizations to the Conici anomaly equations. So when people were studying the chiral ring for dimensional n=1 theories, they definitely studied loop corrections to the chiral ring. You can find operators which are classically chiral, but quantum mechanically not chiral. And so you can compute the action of the supercharge on these operators. The sort of Feynman diagrams and perturbative calculations done here are just a very streamlined version of those calculations and then extended to all the semi-chiral operators. So that'll be sort of the physical perspective on the space of local operators. The physical meaning of the higher operations, it's still something that is a little bit eluding me. So they definitely capture pieces of the OP between local operators. But I would love to be able to say something more precise. So in 2 dimensions, you can study correlation functions on the sphere. Then you can say, okay, the vertex, the vertex algebra structure is really a symmetry of the correlation functions on the sphere. The analog in 4-dimensional equal 1 is a little bit more complicated. You can take correlation functions on hyperkähler manifolds. It might be possible to do correlation functions on more general manifolds by putting certain surface defects, but I don't have a clear picture in mind. But anyway, down to examples: pure gauge theory and QCD. So the thing that I found absolutely striking when we started doing calculation in pure gauge theory is that this theory that was supposed to be holomorphic turned out to be topological, meaning that at one loop, all the derivatives of all the holomorphic derivatives of local operators turned out to be BRST exact. And you can argue that this happens because the holomorphic stress tensor is actually exact in this theory. This is quite an exceptional phenomenon. I haven't found it in other theories, but it seems connected to the concept of confinement, in the sense that once you know that your theory in the ultraviolet is topological, then it better be topological in infrared as well at long distances. And well, we know that the physical theory is gapped, it's confined, all the excitations are massive, and so at large distances, even the physical theory is topological. So you could say, okay, this observation is compatible with confinement. It would have been strange, although not absurd, to find an interesting holomorphic theory in the UV and then a topologic something gapped in the infrared. But I think it's a bit stronger than that, because I feel it gives constraints to what the infrared can be. This is compatible with confinement, but is not compatible with a lot of other scenarios that one could dream about the infrared physics of this pure gauge theory. After all, it tells you that you cannot have degrees of freedom whose holomorphic twist will be not topological. So I find it is very encouraging. So this mathematical tools is telling me something about pure gauge theory, which I didn't quite know before. That there are some perturbative constraints which seem to select confinement as a viable possibility and would eliminate other possibilities. So that seems cool to me. For QCD, we are still at the very beginning of our analysis. The holomorphic twist to the theory turns out to have a 4-dimensional Kac-Moody symmetry, or the 4-dimensional analog of a Kac-Moody symmetry, with a group that is PSU NF/NF. So just to remind you what SQCD is, this is a theory of SUN gauge fields with NF fundamental and anti-fundamental matter fields. And in this, after holomorphic twist, the fundamental and anti-fundamental matter fields sort of get mixed up into a representation of UNF/NF, and then quantum mechanically the symmetry is reduced to PSUNF/NF. And well, what do we know about SQCD? One thing that we expect to happen at small NF, at least, is that there is Cara symmetry breaking, meaning that the SUNF times SUNF symmetry of the UV theory should be spontaneously broken in the infrared. Some local operators called mesons, which are bilinear in current fundamentals and anti-fundamentals, are supposed to get an expectation value breaking this global symmetry. And as a consequence, the low energy theory is expected to be a theory of massless mesons valued in essentially in SUNF, with a left and right action of the two SUNFs. This is what the physics makes us expect. And now I would like to understand better what are the consequences of this physics expectation on the holomorphically twisted theory. So now we have this four-dimensional Kac-Moody algebra with holomorphic currents in the UV, and this must manifest itself in the infrared theory. And if you look at the currents, some of the currents are the mesons themselves. Some are bilinears in mesons, and some look like things that are cubic in mesons. And the whole thing starts looking like a kind of vacuum motor construction for the four-dimensional Kac-Moody algebra. And so I think it would be quite cool if there was some algebraic construction, which again has insights on the infrared destiny of the theory. I mean, I should stress that the representation theory of these algebras, this is the correct term, the properties of these four-dimensional factorization, holomorphic factorization algebras are very poorly studied. So there is presumably a wealth of constraints that could be derived. And what was the original target of our project was actually to find the manifestation of something called cyberduality. Cyberduality is the statement that gauge theories with different gauge groups can actually look the same in infrared. It's sort of the first clear demonstration of the fact that the gauge symmetry is not an intrinsic property of a theory. And in principle, one should be able to take the holomorphic twist of two theories related by duality and find the relation between the factorization algebras. Now, a challenge is that you can convince yourself that non-perturbative effects are really needed for the factorization algebras to match. But computing the perturbative answers is at the very least a necessary initial step to be able to do a comparison. Here I should also point to the physicists in the audience that the local operators which appear in the holomorphic twist are precisely the same as the ones that are counted by the superconformal index. So at the moment, most of our, an important check of cyberduality is that the superconformal indices of two dual theories coincide. And so in a sense, we're trying to categorify that statement and show that the spaces of local operators themselves and not just their order character coincide. And then ideally, even I could even dream of matching the factorization algebra structures. So in a sense, morally speaking, is like, these theories have large flavor symmetries. And, one could dream that it could be somehow characterized as representations of this Kac-Moody symmetry. And then perhaps cyberduality could just be reduced to the statement that two different representations of the Kac-Moody symmetry are actually the same. There is a flavor of level run duality actually in these two. Okay, now the final slide is about something called twisted holography. This will require probably a lot more background that I can transmit at this point. But Kevin has been proposing the idea that the holographic correspondence between physical quantum field theories and supergravity backgrounds or superstring backgrounds should admit a twisted manifestation where you take the holomorphic, you take the twist of some quantum field theories and you match it with some twist of the supergravity theory. So on both sides, there are some simplifications. And so you are supposed to be getting some toy models of holography where you have, just say, this holomorphic twisted theory on one side and some kind of holomorphic supergravity on the other side. And it turns out that although we don't have a very clear holographic dual for the physical theory, here we can find a holographic dual for the twisted theory. So there is a perfectly mathematically well-defined proposal where you take this holomorphic twist of say pure unique one gauge theory, and you compare it with the B model in a certain topological B model, the B model topological string in a certain background. So it turns out that this holomorphic BF theory lives on 4-dimensional branes in C3 in the B model. And so if you backreact 4-dimensional branes in the B model, you get some background which is holographically dual to the holomorphic factorization algebra. And so at large N, you should be able to do calculations on both sides and find factorization algebras which match with 1 over corrections, at least in perturbation theory in 1 over N. And you can even add some extra branes which allow you to engineer QCD. So for example, you can take this B model on C3 with some space filling branes which add holomorphic Chern-Simons theory with supergroup PSUNF times SUNF, and then placing the 4 branes in the background will engineer QCD, and this PSUNF/NF should match precisely the one found in the quantum field theory. And one should be able to then compute perturbatively in 1 over N the factorization algebra structure on the 2 sides. And we are starting to do some preliminary calculations. So I think it is a lot of fun because, as I was saying, you can definitely try to engineer kind of QCD in string theory and M theory. There are beautiful constructions involving the 8 branes in ADS5 times SS5 or whatnot. And people have a certain familiarity on how to study things like chiral symmetry breaking in these holographic models. And I think it would be very cool to do the same in these twisted versions. Well, as I said, everything is mathematically well defined, and holography should be provable as a theorem. And okay, this is more or less all I want to say. I'm sorry I'm 10 minutes early. I badly misjudged the speed at which I would go through the slides.
Great, let's thank the speaker. And so we have time for some questions.
Can I ask a few things? Yeah, so I wanted to ask a little bit about this statement that the pure gauge theory holomorphic twist actually turns out to be topological.
Mm-hmm.
Can I interpret the statement in the following way? So there is a holomorphic L-infinity algebra associated to the pure gauge theory. You're saying that this holomorphic L-infinity algebra is actually quasi-isomorphic to a standard L-infinity algebra.
I don't know if I would call them L-infinity precisely, but yeah, I would say that it's an E3 algebra.
Well, I mean, so you're saying that you're using the word factorization algebra, right? So
yes, I think it's a bit better to use the term factorization algebra rather than L-infinity algebra. Even in 2D, the L-infinity operations are just a piece of the whole E2 algebra structure.
Right. But okay, so in that case, the holomorphic thing is actually quasi-isomorphic to a topological, right?
Yes.
Do you know what the topological algebra is?
No. So, well, we have computed for SU2 the cohomology of local operators up to Gauss number, some level, up to some Gauss number and number of derivatives. We have a large N answer. We have not computed any brackets.
Okay. Is it finite or infinite dimensional? The cohomology.
In perturbation theory, it's infinite dimensional. The index has infinitely many terms.
I see.
I do not know what happens though when non-perturbative effects are turned on.
Yeah, it's quite tempting to conjecture that you would just get the algebra associated to the CPN model for SUN, CPN minus 1 model for SUN, non-perturbatively.
There is definitely some kind of a relationship in the sense that if you take an holomorphic theory in 4 dimensions and you compactify it on a T2,
right,
along the angular directions in each plane, you will get a 2-dimensional topological theory with infinitely many fields, all the Kaluza-Klein modes. And then local operators at the origin of C2 will become local operators at the corner in 2D. And there could even be a fan, a web perspective on that, because this gauge theory will be massive in 2D and there will be massive vacuum and the energy effect is all potential. And now these sort of operations which involve integrals on S3 it should be possible to convert them to statements in 2D, although it takes a little bit of geometry. Paradoxically, it's easier in 2D when you go from talking about vertex algebras is like going from 2D holomorphic to 1D topological because you're looking at the Fourier modes on the circle. Going from 4D holomorphic to 2D topological is a little bit trickier, but I think it's useful perspective. And it's definitely true that, for example, the vacua of 4-dimensional Equal theory are associated to the vacua of the CPN -1 sigma model in 2D when they do this sort of operation. It could be a useful perspective, but I've not looked at it.
Okay. Thanks.
Are there other questions?
I'm just wondering what your point of view gives applied to maximally supersymmetric, like n equals 4 super mills. So what's the right type of questions? What's the point of view?
You can definitely do an holomorphic twist of the 4-dimensional in 4 theory. So this will give you an holomorphic theory with residual supersymmetry. So that, for example, instead of being defined on C2, is more naturally defined on C2/3, if you want. And there are beautiful statements one can try to make about holography of that, and one can definitely study the factorization algebra structure. And it's one of my dreams to say, okay, I compute the factorization algebra structure, I derive information about the local operators, and then I feed it to the bootstrap or some other, very physical construction. There has been a history of protected calculations being used to determine the physical theory, actually using the bootstrap program. So definitely, you can study the holomorphic twist of the 4D Equal 4 theory. A lot of this perturbative structure I'm discussing seem to drop out. So as far as you can see, but we're not certain yet. At least in examples, it looks like the higher loop differentials actually act trivially on the 3-level cohomology. So it might be that things are much simpler in Equal 4 super mills, but I'm not certain of that. There are tantalizing hints that go back to work by Sheen and one of his students, where there's, because amusingly, as I was saying, there are some. So physicists had tried before to study the cohomology of local operators without using this holomorphic twist perspective. They did mostly 3-level calculations. What this perspective allows you to do is to have a very precise handle on the perturbative corrections to that. But in the past, people had definitely computed the 3-level cohomology of local operators in 4D Equal 4 super mills. And what we can try to verify is that perturbative corrections do not affect that. But we are still not sure that's. So I don't know an normalization theorem at the moment. We only have some very experimental evidence or large N.
It just structurally, the structure of the so-called integrants in N=4 super mills, it looks like a solution of some master equation, but I don't think this is made precise or something. It's
I've been.
well, it's not a precise statement.
No, that's true. But so definitely, for example, when you study the renormalization of quantum field theory, you do write down certain relations based on the whole algebra of Feynman diagrams. And in these holomorphic theories, somehow the renormalizability of the theory is necessary in order to be able to write down a factorization algebra. So I can imagine that just the very renormalizability of the theory would give you the relations which then which we are discussing here. And that perspective might give some analogy with physical theories, but I'm not sure.
There's also some mathematical theory which I call quantum Huchfield theory. So some kind of machine which takes as an input complex varieties and let's say local system or D models and produce out of them some select correlation functions, and they can put together to satisfy equation like that. And more precisely, that type of equation is a master equation for some.
Yeah, I want to ask you if I take the manifold to be C2.
It always compact manifold, so C2 means that
CP. Okay, it could be CP. Maybe it could be CP2 or.
No. I can't say anything on the spot, but the input is similar, but I don't know.
Yeah.
Any other questions for the speaker?
Yeah, I have a question, although I can ask Davide questions anytime. How special is this to complex dimension 2?
I think the general, a lot of the combinatorics just depend on sort of how many directions are Q exact. So 2D topological or 3D holomorphic topological or 4D holomorphic have all some resemblance. If you want to look at, say, 6 holomorphic Chern-Simons, so things that have sort of three exact directions, then I guess you would have an analogy between that or 3D unequal 3D topological theories. So there should be, okay. So the general strategy to get Feynman diagrams which build the factorization algebra is universal, presumably to all holomorphic topological theories. This simplification to Fourier transforms, I think might happen in 6D in holomorphic Chern-Simons theory as well, but I've not looked in detail.
You could dream that if you did this on twistor space, your vague analogy to the amplitude-dehedron might be more precise.
That's true. I don't know. That's true.
All right. Well, let's thank Davide again. And we'll start again at 2 o'clock with Kevin Costello's talk.